Okay. So how is everyone today? Another one because the camera's on now. So any questions about the math we discussed last time? We were talking about how to use the multiply a natural and real, and also raise a real to a natural exponent, using those to make it to where you can do the same thing even with integer, so that you could multiply an integer and a real. By the way, what's the distinction between integers and naturals? Integers can be negative. So the main trick there, the main idea, is that, well, if you wanted to do -5 multiplied by x, then -5 is an integer, and you reduce the problem to a previously solved problem by saying, well, instead of doing -5 times x, I'll do 5 times what? Times -x. Good. And then we talked about the pyramidal numbers also. This is all fine? Okay. So, for a little bit today, we're going to talk about intervals. 15. So this is things that you already know. So we have the following definitions. Let A and B be in the reals with A less or equal to B, so that A is at most B. Then this definition, A, B in square brackets, means what? Very good. So it's the set of all x in the reals such that A lesser equal x lesser equal B. Okay, so this should be no real surprise. We'll do the others very quickly. So A, B, like so, where A has a parentheses and B has a bracket. What does that mean? Very good. So this is the set of all x in the reals such that A strictly less than x lesser equal B. The other way around. And the set of all x in the reals such that A less or equal x strictly less than B. And finally, if they both have parentheses, then this is the set of all x in the reals such that A strictly less than x strictly less than B. So I have a question. Is it possible, but according to the way that we've defined things, for any of these sets to be empty? Yes. So can you give me such an example?
The bottom one is A equals B.
Right. So, for example, note, for example, that the set, say, 3 to 3 with parentheses on both parts. This is the empty set. And by capital Phi, I mean the set that contains nothing. Empty set. Because there are no x's in the reals that are both greater than 3 and less than 3. Are there any others? Any other kind of possibilities where the set could be empty? Sorry?
If it's I,
What do you mean I?
like the imaginary.
But these intervals are subsets of the reals. The complex numbers are interesting, but we're not talking about them yet. What about this one? 3, 3. Is this one empty?
Yes,
It is empty. Why is it empty?
because you're setting it to not be, to bring on the left side.
Right. So the request is for, well, tell me some numbers that are greater than 3 and less or equal than 3. Well, there aren't any numbers that satisfy that. So, etc. Okay, interesting. Okay, remark. This is intersection and union. So, given two sets, given sets A and B, these don't need to be subsets of the reals, but that's the main application we're going to use. Given sets A and B, the intersection of A and B is the set which contains all elements which are in both set A and set B. Okay, so the key for intersection, the keyword is and. How is intersection denoted? So we don't have to write out the word intersection, right? So it is denoted A intersect B. So in English, out loud, that symbol is pronounced intersect. Well, as far as a Venn diagram is concerned, if this is set A, this one is set A, and this one is set B, then visually speaking, where is the intersection? That little American football shaped thingy in the middle. A intersect B is this one. The one that looks like that. Fine. 2. What's the counterpart to intersection? Union, right? It's even written there. So similarly, the union of A and B is the set which contains all elements which are in set A or set B. So the key word for union is or. And so, since this is a math class, and also because we're doing programming and the computer scientists also do this, you should be aware that in English we have this word or. The name for it is called a disjunction from a math point of view, or. And when I say in set A or set B, when a mathematician says or, they mean that the first thing could be true, or the second thing could be true, or they both could be true. It's fine. That's a little bit different than the way or is used on the street, or like when you're talking with your family. Often, or means this one, the first possibility, or the second possibility, but not both. So, for example, if you say to a child, you can have cake or you can have ice cream, that means that among your choices are that you can have cake or you can have ice cream, but it is not permissible for you to have both. But when you say that, when you use mathematicians or, and you say you can have cake or you can have ice cream, that means that it's also possible for you to have both. Okay, so and this is how my children respond. Okay, great. So so that further raises the question, if or means first choice or second choice or both, then what's the name for first choice or second choice, but not both? Exclusive or. Okay, that means that you can have the first one or the second one, but not both. So or means, this is mathematicians or. Fine. So then, concerning a Venn diagram point of view, A, B. Well, I call it mathematicians or, but you should but the rest of the point is that is also how computer scientists reckon the word or when they're being technical. So then what is the, next question is, how is union denoted? Good. So very similar to intersection, except now it's would hold water instead of the other way. And then if this is the concerning Venn diagrams, what does the union look like? Right, the whole shebang. So A union B would be, I write equal. That's kind of sloppy, but I think you take my meaning. Is that thing. Okay, and we'll go ahead and do the last one. 3, the symmetric difference. Difference of A and B is the set which contains elements from set A XOR set B. Okay, so then XOR means what? Or sometimes it's pronounced ZOR. Exclusive or. That means that this is the when you're talking to a typical child and you say cake or ice cream. So if you were a mathematician talking to them, you would say cake, ZOR, ice cream. Okay, because that's what you mean. just the one or the other, but not both. The notation for exclusive OR is not quite as uniform as intersection and union. We'll denote it in this way. A, and then delta is probably good. B. D for difference. It's called symmetric difference because asymmetric difference B is the same as B symmetric difference A. That is in contrast to subtraction, where A subtract B is almost always not B subtract A. So like 3 subtract 5 is -2, but 5 subtract 3 is +2. So from a Venn diagram point of view, if this is set A and set B, then what does the symmetric difference look like?
Football cut out.
Yeah, the football's cut out of it. I like it. So it would be like this one. So, well, okay, I'll draw it like this, and I'll shade in the part that is present. So the part that is present is like so.
So, is it denoted across mathematics that way with delta? Or?
Not in every conceivable situation. The most common symbol I've seen is delta.
Okay.
And just be aware that it's symmetric. That is to say, A delta B is B delta A. Okay, so any questions about these? These are all things, with the exception of the name symmetric difference, these are all things that the state of Texas says you knew before you got here. Okay, so let's have an example. Please simplify. How about 2 to 13 intersect? How about, say, -5 to 8? Okay, now, some of you can do this in your head. That's fine. So, but the point is that we want to figure out a way to get MATLAB to do this, right? So we need to think what kind of thing could we do to make it to where MATLAB could do this in a program that's manageable. All right. So here's one way. This is the best way I've found to teach math students to do it. Well, so I'm going to take the first interval, 2 to 13, and I'm going to make a copy of the reals here. And I'll take the second interval, -5 to 8, and make another copy of the reals. And now there's 4 numbers, 2, 13, -5, and 8. And we're going to plot all of those numbers in appropriate positions. Their absolute positions are not important, but their relative positions are important. So of the 4 numbers, 2, 13, -5, and 8, which is the least? -5. So I'm going to plot it here. And then in the convention of plotting intervals, what do I need to do with this? I need to fill it in because that indicates that it is present. Okay, so now there were 4 numbers and now there's 3. Of the remaining numbers, which is the least? 2. So I'll plot it and I'll plot it up here on this one. And again, I'll fill it in because that indicates it is present. Of the remaining numbers, which one is least? 8. I'll plot it down here and fill it in because that indicates it is present. So what I'm saying is now this interval is all of this. And I'm just making the wavy line because otherwise you wouldn't be able to see my pen. Of the remaining numbers, which one is the least? 13. And I'll leave it open because that signifies its absence. Okay. So, intersection. That means we want all of the points that are in the first interval and the second interval. So suppose we're back here, like at negative 7. Is negative 7 in the intersection? It is not, right? Because it's not in both sets. How about like right here? This is like approximately 0. Is 0 in the intersection? It is not. It is not because we're looking for all the points that are both red and green. And even though this point here is green, it's not red. So it's not part of the intersection. Where does the intersection begin? At 2, right? You can see there, that's when we finally have a point that is red and green. And then, so we still in the intersection, right? And then it ends there at 8, right? So this sort of visual method, humans are quite good at a visual method like this. So from here, I think you can probably just tell me the answer. What is the intersection? Closed at 2 and closed at 8. Very good. Any question about this? Okay. How about the same intervals? But now I want you to do 2 to 13 union. Negative 5 to 8. And with the same picture, I think you can tell me the answer. So again, intersection, the keyword is and. What is the keyword for union? Or, and remember this means mathematicians or. Right. So back here at, say, negative 7 is not in the union because this point is graphite colored. Okay, it's not green, and it is also not red. So it couldn't be in the union. So negative 5 is in the union because it's green, and that's enough. It has to be just green or red. So negative 5 is where the union begins. So we're in the union. Oh, this one's red also. Is that in the union? I thought it was or. Ah, but you can have both, right? Because that's what mathematicians or means. Okay, so then Okay, where does it end? Open at 13. Any question about this one? Okay. 2 to 13. Symmetric difference. Negative 5 to 8. Okay, and I want your answer by simplifying a symmetric difference. I want the answer to end up being a union. Okay, so then now, what is the key word for symmetric difference? Exclusive or, XOR if you like. So that means that we're looking for points that are green but not red, or what? Red but not green. Okay. So then again, back here, these graphite colored points, they're not what we're talking about. So we need to proceed forward until, okay, right there. So that is a point that is green but not red. So part of the symmetric difference starts at 5. Negative 5. Then I can see that there's a bunch of points here that are green but not red. So how far does this bit of the symmetric difference proceed? until 2, and then is 2 part of it, or is it not? It is not. So 2 is not part of the symmetric difference because 2 is green and red, and we need it to be just one or the other. Fine. So then none of this stuff in the middle is part of the symmetric difference because that's green and red. Where does the next bit of the symmetric difference begin? At 8. And is 8 part of it or not? It is not. So then we'd have 8. So open at 8, and then it proceeds to where? 13, and it's open at 13. And then what needs to be written here? Union. Any question about this? 8 is not in there, so do you agree that 8 is colored red? No, I think it is, because is 8 between 2 and 13? Okay, so this is 8. The symmetric difference are points that are green but not red, or red but not green. So just one color. So can we agree that 8 is green? And 8 is also red. As a result, it can't be part of the symmetric difference. Other questions? This is okay? Okay, how about another? How about, please do the following. So, no, I'm going to make a slight remark. A union of intervals can be simplified when there's kind of two conditions, two possibilities. When what? So what I mean is, like, consider this example. We were able to simplify that union in the sense that the right-hand side of this equation is simpler than the left-hand side. Okay, so then what property of this circumstance allowed that to occur? An overlap. Right? So when the intervals overlap, but there's actually another possibility. Can you think of it? What's another possibility? Well, even if they have one point in common, then they overlap. So by overlap, I mean they have a non-empty intersection. But there's even another possibility. How about this one? Or how about A to B union B to C? So do these, is that focus? Not really, is it? How do I make it focus? Is that any better? Is it getting better or worse? Oh, that's worse. Y'all can see that? Okay. So, do these two intervals have a non-empty intersection? No, right? There's no points that are in both. So they don't overlap, but they can be glued together, if you take my meaning. Good? Any question about that? Okay. So, next example. How about please simplify or confirm that it's already simple how about 2 to 17 union 20 to 30 and 2 to 17 intersection 20 to 30. What do you think? So the first one can't be simplified. It can't be simplified because the interval on the left argument to the union, has elements at most 17. So if this were red and this were green, it would be like these, except they're pushed far apart and they don't overlap. So this one, so we want to show that this one cannot be simplified. How about this one? Can this one be simplified? Yeah, it's the null set, the empty set. Well, so then we could do that just very rapidly now. So 2 to 17 will be that one, and 20 to 30 will be this one. The situation looks like this. Right, so there are no points that are both red and green, so the intersection is empty. And these intervals are not overlapping, and they also don't have this property, that it's like one single interval that was cut at B, and B was given to just one, but not the other. As a result, this is already simple. Any questions about the intervals and things like that? So I've shown you a way for human beings to think about it. And I'm purposefully leaving it a little bit open about how you might achieve the same thing on MATLAB. Okay? So, that being said, now we need a few other definitions. Let big X be a set. Well, I'll say let big X be a subset of the reals, like so. Then the min of X, of set X, is defined as follows. How can we define it?
Where every, so it'd be like A would be min, you could do is less
So the min of x, min of set x is A, and now what qualifications do we need?
Where it's less than x and x.
Okay, where where A is less than x, less or equal to x
And X is
For every x.
for all x and x. We talked about this already, right? This one? Okay. So this is not quite right. Something is missing. So this part is good. It needs to be the case that A is less or equal to every little x for every little x in set x. But something else needs to be true also. A must be in there. So where A is in set x and A is less or equal to x for all x and x. Okay, as a result of this definition, the empty set, minimum is not defined for the empty set. It's not defined. It's not defined because, well, there isn't, you can't even get started because there is no element in the empty set. So, note, the minimum of the empty set is undefined. Well, fine. So how about maximum then? The maximum of set x is what? Is some number b where what? Where b is in set x and what? B is greater or equal to little x for all little x in set x. And again, note that the maximum of the empty set is undefined. Well, now I have a question. Is it the case that every subset of the reals has a min? No. No, right. So, as a remark, we'll extend slightly our definition of intervals. So in the first place, please recall that negative infinity and positive infinity are not real. They're not in the reals. What they are is they're some other kind of thing, and they're comparable to reals. And every time you compare negative infinity to any real, negative infinity is strictly less than that number. And every time you compare positive infinity to a real, positive infinity is strictly greater than that real. Are not in the reals. So 2, this is another way to write an interval, so negative infinity to b, for example. So this is an interval. It means what?
Means everything less than.
Very good. A set of all x in the reals such that x is less or equal to b. Now, another way to write this, because it's nice to, when you're dealing with intervals, to have the x between two things. Notice that x is not between two things currently. You could alternatively write the inequality in this way. Negative infinity less than x less or equal b. You could write it like that. So now x is between two things. That's kind of nice. Because of 1, the statement negative infinity to b is nonsense. Why? What would this mean if it could mean anything? Yeah, that negative infinity is somehow in there. But that's not right, because negative infinity is not a real, and an interval is a subset of the reals. So this is nonsense in the same kind of way that if you were to go to the grocery store today and buy a bag of apples, and then you take it home, and then you finally look carefully, and you look inside and you find chicken, right? Wait, that's not supposed to be in there. Under no circumstance will that be correct, to take a bag of apples home and then to discover that there's a chicken in there. Okay, same thing. This is nonsense, because negative infinity is not a real. Okay, so I have a question. What is the minimum of the interval, say, 3 to 10? 3. Not very difficult to imagine, I think. Well, how about this one? The minimum of negative 3 to 10. It's undefined, right? It's undefined. Now let's examine this carefully. So the reason why is the following. So we could look at the interval negative 3 to 10. Visually. Okay. And then the request is we want to find a red point. We want to find a red point that's less or equal to all other red points. So could negative 3 be the answer? No. Why not? Because it's not red. Negative 3 is not red, so negative 3 is not the answer. Then you might say, oh, okay, well, I'll just move a little bit to the right. Okay, so suppose that you put on offer a point that's just a little bit to the right. Then I'll get out my my math eyeball and I'll look at what you're looking at very closely. That's my artist's impression of an eyeball there. And when you look at it close enough, you know, here's negative 3. And then I'm looking at it so closely that 10, in fact, is miles and miles that way, just miles. This is all the way over there. Can't even see it. And then when I look closely with my math eyeball, you're actually pointing at that point right there. Is that the least red point? No, there's clearly other red points that are less. So the thing is that no matter what red point you point at, you have to be some distance to the right of negative 3, and that couldn't possibly be the least red point. So is there any question why this has no minimum? So is this the only way in which an interval could have no minimum? And it could be unbounded below, right? So, for example, the minimum of negative infinity to 10, like so, is also undefined. Any question about these things? So, depending on where you are in your math career, so, you know, this interval here does not have a minimum. It doesn't have a minimum, but somehow, even though negative 3 is not the minimum, negative 3 is still kind of important, and we'd like to be able to point out and say, somehow, negative 3 is important in such and such a way. So even though negative 3 is not red, negative 3 also, negative 3 does have the nice property that among all real numbers, it is the largest real number that all red points are greater than or equal to. So, for example, here's a point right here. All red points are greater or equal to this point. And all red points are greater than or equal to some point way over here. And all red points are greater or equal to that point. Among all the possibilities that every red point is greater than or equal to, which is the greatest? Negative 3. Negative 3 is the largest real that all red points are greater or equal to. So does anyone know the name of what I'm talking about? Yes. Infimum. So, definition of infimum and supremum. I'm not sure that's how you spell it. That one looks good. There's an I here? Okay. I'll go with the democratic process here. Infimum. Okay, so let set X be a subset of the reals. Then the infimum of set X is some value A. And what needs to be true about A? So in the first place, does A need to be in set X? It does not need to be. So this is, infimum is like minimum, but just a little bit. The first way in which it is not the same as minimum is that the infimum doesn't need to be in the set. So where A is a real number, and what? A is less or equal to little x for all x in big X. But that's not all, because right now, I could be, this point would satisfy. Because this point, what I'm pointing to is real, and it's also less or equal to every red point.
You just say it doesn't have to be in the set.
Well, we need
Of X.
A to be real, A has to be less or equal to every point in the set, and furthermore what?
You add like any number,
A has to be greater than or equal to X not X.
Right, I'll say, and A is greatest. I'll say it like this. And A is greater than or equal to C for all C which satisfy the first two conditions. So A is greater than or equal to all possibilities. Okay.
Would you have to clarify that C needs to be underneath the set? Couldn't you have-
Well, that's what this means.
Okay.
Okay, the counterpart to this is supremum, denoted sup. So the supremum of X is a number B, where, well, in the first place, B has to be real. b has to be greater than or equal to x for all x, little x in set x. And what? B is less or equal to C for all C, which satisfy the first two conditions. Okay. Notably, is soup defined for every subset? Or inf? Doesn't matter.
Say that one time, I'm sorry.
So let x be a subset of the reals. Is soup of x always defined? No. So for example, well, soup of, let's consider, note, the inf of the empty set. Let's think about that. So we want a number that's in the reals that's less or equal to everything in the empty set. Well, okay, that's trivially true. Every real is less or equal to everything in the empty set. But then now, among all the possibilities, we want a greatest one. So is there a greatest? There is not. So this is undefined. And there's other issues too. The point of infimum and supremum, the only thing that I want to make is that while the minimum of interval -3 to 10 is undefined, what? The infimum is defined, and it's -3. Okay. Fine. So now we've got these, the point of this discussion is to draw out the fact that minimum and maximum are a little bit slippery, right? They don't always need to exist. So, I have a question. What about, say, the minimum of the integers? Is there a minimum integer? There is not. What about the infimum of the integers? It's undefined. Sad. What about the minimum of the naturals? Is 0. Because recall that in our class 0 is natural. Okay. When a minimum exists, the infimum is also that exact value. So the infimum also exists. What about 4? What if we say that set X is a subset of the integers? So just some subset of the integers, and we're asking about. So let that be the case, and we're asking about this, the minimum of set X. Does that need to be defined? It could be defined, conceivably. So, for example, if the set, if set X is the set which contains 23 and 70, and nothing else, then the minimum is defined. But is every subset of the integers have a defined minimum? No, right? Because the integers are a subset of the integers, and it has no minimum. Okay. So this is not always defined. And this next one is the big bad tool that we're going to use for the next couple lectures. So let set X be a subset of the naturals. So now we have a subset of the naturals. And now I'm going to ask, what about the minimum of set X now? Under what circumstances does the minimum exist?
If, it's closed.
Well, set X is a subset of the naturals. So as a result, every subset is closed in the sense of
I don't think that's.
closed and open. So
Yes, it exists.
So, yeah, as long as
does the minimum exist for every subset of the naturals? Ah, for every non-empty X. So this exists for all X which are not the empty set. So this last item, the fact that every non-empty subset of the naturals has a least element, has a minimum. This is so important that it's given a name. Does anyone know the name of 5? What is it? Someone said it.
well-ordered.
The well-orderedness of the naturals. And in the end, all semester long, on all the things that we've done, we've been using the well-orderedness of the naturals on essentially every assignment that we used recursion on. So the thing about the recursions that we're doing, like multiply a natural and a real, where we said, okay, I want to multiply 5 times x. Well, that's actually x plus 4 times x. And that's actually x plus 3 times x. And that's actually x plus x plus x plus 2 times x, etc., all the way down. And that coefficient on the x, it's counting down in the set of naturals. Well, is there a least natural? Yeah.
Yes.
That's what means that the process is going to stop. That's what causes the algorithm to actually terminate and work. The well-orderedness property of the naturals. Okay, so now we have a name for this thing that we've been using all along. Okay. Good. So on the homework that's due today, is this the one I think it is? No, it's not. On homework we already turned in. We talked about the parity homework, where we talked about Euclidean division, but with the specific case of when the divisor is 2. So let A and B be natural with B not 0. Okay. Then there exists a Q and an R in the naturals such that A is B multiplied by Q plus R, and 0 is less or equal R less than B. So we don't have enough time to show everything today, but we can start naming some things. So what we're doing is we're dividing A by B. So that's why B has to be non-zero. You're not allowed to divide by 0. So Q and R, what are their names? Quotient and remainder. And this is a formalization of the grade school thing where, because you can even teach this to young children quite easily. You can say, well, divide 23 by 4 and tell me the quotient and the remainder. And if you just tell a 5-year-old to do that, they'll be like, nah, I'm probably not going to do that. But if you state the problem differently and you say, here are 23 M&Ms. I want you to make groups of size 4. And I want you to tell me how many groups you can make. And I want you to tell me how many are left over when you're not able to make another group of 4. And if you do it correctly, I'll let you eat some of the M&Ms. Now suddenly the 5-year-old is a scientist, right? We're serious about this problem. Okay, so then if you divide 23 into groups of size 4, how many groups can you make? 5 groups. That's the quotient. And when you have made 5 groups, how many are left over? 3. That is the remainder. Notably, 3 is less than 4, which was the group size. Okay, that's all that this is saying. This is like the grade school break M&Ms into groups thing. But it's just couched in this language. So this is called a Euclidean division. Euclidean. Euclidean division, and moreover, the Q and the R, not only do they exist, the Q and the R are unique. So one of our upcoming programming tasks will be to write a program which, given A and B, computes Q and R. Okay, so have a nice Thursday.